Good afternoon. Unfortunately, I didn't record last time I was in here, so I'm going to go through this again. When we look over here with the 2f of x, we are running it through the function and then multiplying that function by 2. So when we run minus 5 through the function, we get 2. Multiply that 2, 4, 0. Try that again. 4, 0, 4, 6, 4, 0, 2, 4. Sorry about my plotting. So we have a graph. That's going to look something like this. Now I'm sketching it. And my system is out. Okay, so describe the transformation. This is a stretch by 2. Now we're going to call that a stretch by 2 in the x-axis, vertical, because we've changed the y-coordinates. We have 2 invariant points. We have negative 4, 0, and 2, 0 are invariant points. They stay the same. The domain is going to stay the same. It went from negative 5 to 6, inclusive. The range is what changed. In the original graph, it was 0 to 3. In this graph, it's 0 to 6. We're going to do the same process when we take this. We run the function, our input number through the function, and then multiply by half. So we end up with 1, 0, 1, 1.5, 1, 0.5, and 1. So again, those are just half of the original output numbers here. Our sketch is going to look something, and my board is becoming annoying. I may have to change that. Okay. So, looks something like this. Okay, give me a second. I'm just going to fix the board because I really don't want to restart the system. So the transformation is a vertical stretch by a factor of 1/2, and again, it's in the x-axis. Because we can stretch it around any line that we want, but we are only, by curriculum, only going to stretch it around the x-axis as we talked about with reflection. Our invariant points again are negative 4, 0, and 2, 0. The domain stayed the same, negative 5 to 6. The range became 0 to 1.5. Okay, so the other way that we can write these two is we can write this function, 1/2 y is equal to f of x. And this function can be written as 2y is equal to f of x. Notice the stretches are different or this looks different. We can't get the stretch directly from these guys without either taking the reciprocal or moving it to the other way so it looks like this function here. Okay, we already talked about what type and around what line. This is a little different. We're going to talk about f of 2x. Now, if you think about this, we are taking something, the input number, multiplying it by 2, then that input number goes into the machine that's going to give us the output number. So the machine takes -5 and gives us 2, takes -4 and gives us 0, and so forth. So to get the same output for 2, I need to plug -5 into this machine. Well, to get that, I only need -2.5 being my input number. -2.5 times 2 gives me my -5, which is then fed into the function. The same thing for this. I need to plug in -2, and if I plug that in, I will get out the output number is 2. Well, I only need -1 to do that. So I'm going to take each of these input numbers and have half of them. That one doesn't change, and we have 1, 2, and 3. So when we plot this, we're going to end up with a graph that looks something like this. So again, it has to do with this rule. I need that -5 to get out 2. Well, I only need 2.5 multiplied by that 2 to begin with, then we can take the input number of -5.
Good afternoon. Cross Country Running Club begins Thursday at 3:45. Please come prepared to run. You will need appropriate running shoes and clothing. Please sign up using the Google Form link or the QR code posted. Also, we missed one birthday announcement this morning. Happy birthday to Kyla Hammermaster. Have a good afternoon.
So we have a horizontal stretch by a factor of 1/2 in the y-axis. The graph gets smaller by a factor of 1/2. Again, that 1/2 is the reciprocal of 2. The only invariant point that we have is 0, 2. The domain is now -0.2.5 to 3 inclusive. And the range stays our 0 to 3 because we didn't change anything vertically there. What happens here? Well, now we're multiplying the number. That's going to give us our input number, which is going to go into the machine of fx. So again, to get the first guy, to get out the 2, we must plug in -5. Well, the only way I'm getting -5 out of this is if I plug in -10. So each of these these original input numbers, we have to have twice as much. Okay, so each of these again. So each of these numbers in this line gets multiplied by a 1/2 and then fed into the function that's going to give us that 2. So we end up with a graph that looks something like that. It's a very rough sketch, and I'm not going to spend much time on it, but you get the general idea. Every point is now twice as far away from the y-axis as before. So we can call this a horizontal stretch by 2 the y-axis. Again, the invariant point is 0, 2. The domain is now -10 to 12. And the range stayed the same at 0 to 3. So what we have is we have 3 different ways to talk about this. y is equal to a times a function, or y divided by a is equal to that function. Or we can say replace y with y over a. And if the a is written in those spots, all of these are the same. If a is greater than 1, we talk about expanding the graph. So we're taking the graph and stretching it outward from the y-axis. If a is between 0 and 1, we are taking the graph and we are compressing it towards the y-axis. If a is also less than 0, so here if it's -2, we treat it different. We treat it as a 2, and then we treat it as a negative. It has a reflection, as we talked about the other day. The horizontal stretch only has 2 real ways to describe it. We can write it as an equation, y is equal to f of b of x, or replace x with b of x. Here we have a horizontal stretch by the reciprocal. Again, because you need to plug things into the function rule, function machine, the stretch is opposite what is inside, or opposite is the reciprocal of what's inside this b of x. So if b is between 0 and 1, we have an expansion. Again, sorry, I gotta go back. Here we're going to the y-axis. Got that wrong. This way. And if b is greater than 1, we are talking about a compression where we have this. And then b being also less than 0, we have a reflection. Now, I did everything right up here except I used the wrong axes on here. Recording. So, can you come back later, please? Just leave it in my mailbox. So when we're talking about an expansion in a vertical, it would be expanding in this direction. And a compression would be expanding in that direction. So, going back to that idea. First of all, I am changing the x. And that's always going to be horizontal. In this case, it's horizontal stretch by 2. It's always the reciprocal of what's next to the variable. Now, same thing applies to y. We just don't always write it that way. We have to write it that way for this one. And in this case, in the y-axis, we are always stretching it around this. Here, I've given you a function. It's an exponential function. I've taken x. I've replaced it with 3x. So horizontal stretch, horizontal because we've dealt with the x. Now in this case, it's by 1/3. It's always the reciprocal of what's next to the variable. Over in this one here, we have -2 times our function. So we are first doing the function and then multiplying it by -2 for every of the y coordinates. We have two transformations. We have a vertical stretch by 2, because it's outside the function, and it's not next to the variable, so we just read that in the x-axis. And we have a reflection in the x-axis because of the negative sign here. Now I could read this right now as, okay, it's next to the variable, so I need to have the reciprocal of that number. Or because it's a y value, I can divide both sides by 3 and write the equation like this. So here we have a vertical stretch. It's outside the function x cubed, so that means it's vertical, by 1/3. Looking at this number here, or the reciprocal of that number there. And again, in the x-axis. So we always have to say where we're reflecting, or in this case, stretching. Here again, we have 2. We have the number 2 outside the function, and we replace the x with 1/3 x. So a vertical stretch by 2. Again, it's outside the function, so that means vertical. We have a horizontal stretch by, okay, well, it's inside the function. It's next to the variable. So it's the reciprocal of that number, 3, and in the y-axis. Again, because we stretched it here, or inside, we always take the reciprocal. If I had written this as 1/2 y, I take the reciprocal of the 1/2 to get the 2. I didn't in this case, but that's generally the other. Always take the reciprocal when it's next to. Here, we're inside the function, next to the variable x, that's always horizontal. So we have a horizontal stretch by 1/2 next to the variable, we'll take the reciprocal. And we also have a reflection in the y-axis, a horizontal reflection where it's going to flop across the y-axis. Describe the function, describe the changes to the graph if the following changes are made, write the new equation. So we're going to replace x with 4x. So here is the new equation. Oh, that's not the new equation. That's the new equation. Okay. So we've replaced x with 4x, so we replaced x, so that's horizontal, stretch. And again, it's next to the variable. So we take the reciprocal, y 1/4 in the y-axis. Here we have 2. We are going to replace x with negative x and replace y with 4y. So 4y and negative x squared plus 3 times negative x plus 2. You may want to write it this way. But it's going to get the same answer in any case. You replaced y with 4y. Vertical stretch by 1/4. Again, next to the variable, take the reciprocal of that number. And you can see what happens when we divide it by 4, we end up with the 1/4 in front. We have replaced x with negative x, so that's a reflection in the y-axis. Because it's a horizontal reflection, we're going to be slipping across the y-axis in that case. Replace y with 6y, replace x with 1/3 x. 6y is equal to 1/3 x minus 3 over 2 1/3 x minus 1. There's an equation. It's not very tidy, and I'll show you how to tidy it up later at another time. So all we want is, what did we do? Well, we took y, replaced it with 6y. Vertical, because of the y, vertical stretch, by the reciprocal of that number. Again, it's next to the variable, so take the reciprocal of that number. And all our vertical stuff happens in the x-axis. We replaced x with 1/3 x, so horizontal stretch because we're fiddling with the x. Again, it's next to the variable, so we're going to take by 3 in the y-axis. So here I give you the last way is I describe the stretches, and I need the equation. And possibly the mapping notation also, but we're just going to do the equation. We stretch it vertically. Okay, I've done something to the y. Y has been replaced with, okay, around the x-axis by a factor of 3. I can replace y with y or 1/3 y. Also, because I'm vertically stretching it by a factor of 3, I can just take the function and multiply it by 3. Stretch horizontally, so I'm going to do something to the x and I'm going to stretch it by a factor of 3. So again, I have 1/3 of x. So 2 ways to write this equation. Y is equal to 3 tangent 1/3 of x, or y over 3 is equal to tangent 1/3 of x. Here we have a horizontal stretch and a reflection. So we're going to replace x with negative x for the reflection. And then we're going to replace every place we see an x in that with 5x. So I'm going to replace the x with negative 5x in every place I see that x. Perfectly valid way of writing it. I'm going to write it as 1 plus 5x over negative 5x. I hate negative signs on the bottom, so I'm going to rewrite that as negative 1. Oh, I'm going to erase that. Negative 1 plus 5x over 5x. I just don't like negative signs on the bottom. There's your homework. I hope this worked.